Okay, I think it's working. Hello, welcome back finally to AP Chem. We're gonna pick up where we left off on Friday. I'm gonna do a quick recap of like the last few things we had talked about on that Friday in this lesson, just so that it's not completely brand new information. We were talking about solutions and how solutions are homogeneous mixtures between a solute and a solvent, and that solute and solvent don't necessarily have to be two liquids. It could be a liquid and a gas, or a gas and a gas, or a solid and a liquid, or even a solid and a solid. It really doesn't matter what the phases of the solute and the solvent are. As long as it is a homogeneous mixture, we can refer to it as a solution. Now, most solutions are between liquids and either a solid, or liquids and a gas, or liquids and a liquids, which is the most common kind of solution that we'll talk about. But when making a solution, there are three basic steps to the formation of the solution, which we talked about on Friday, 2 Fridays ago. So step one was about separating a solute into its individual components, or expanding the solute. Yes, that was a burp. Anyway, expanding the solute. So let's say your solute is salt, NaCl, sodium chloride, table salt. Table salt is an ionic compound. That means that sodium and chlorine are held together by ionic bonds, very, very strong attractions. To separate salt into its individual components, which is sodium and chlorine, we have to overcome that ionic bond that's holding them together. We have to break apart the salt into sodium cations and chlorine anions. And we have to overcome that attraction that's holding them together, the positive and the negative. So that takes energy, because breaking a bond requires energy, just like breaking a stick requires energy, just like breaking a bone requires energy. Any type of bond breaking requires energy. So step one is going to require an energy input. For step two, we're overcoming the intermolecular forces in the solvent. So it is very, very similar to step one. Instead of overcoming intramolecular forces, I use the word intra here to refer to a bond holding a molecule together. So intramolecular forces is something like a covalent bond. It holds atoms within a molecule together. It's not between one molecule and another molecule. A force that's between one molecule and another molecule is an intermolecular force. So intermolecular forces, I'm going to draw some examples down here. Water is a great example of a solute that we're going to commonly use that has very strong intermolecular forces. The water molecule is a very polar molecule. It's got some lone pairs in there that are not symmetrically distributed around that central atom. So we have a net negative charge, or a negative dipole, or partial negative charge. There's a lot of different ways that you could describe it on the oxygen side of the molecule. And then we've got a net positive side on the hydrogen side of the molecule. And it really has to do with those lone pairs and the fact that these bonds between hydrogen and oxygen are very polar. In fact, it's one of the most polar covalent bonds that you can make, because hydrogen is very weak in electronegativity and oxygen is very strong in electronegativity. It's so polar that when these water molecules get around other water molecules, we start to see an attraction between the negative dipole and the positive dipole of other water molecules. So I've drawn two water molecules here. What I'm not drawing yet is the attraction between that negative dipole of the water molecule I've drawn below and the positive dipole of the water molecule I've drawn above. I'm going to do it in a different color here. There is a force of attraction between here and here. And there's going to be more forces when I start adding more water molecules. So if I added another, boom, boom, this oxygen is going to be attracted here and attracted here and attracted here. And eventually you're going to start to see that the water molecules behave kind of funny because they're always trying to orient themselves where one positive dipole is near a negative dipole because there's a force of attraction there. Now, because these bonds are so polar, we refer to this dipole-dipole attraction or dipole-dipole interaction as hydrogen bonding. Hydrogen bonding occurs when you have a hydrogen atom bonded to a very electronegative element like oxygen, nitrogen, or fluorine, and you create such an extremely polar molecule that the dipole-dipole interactions are very, very strong. They're the strongest kind of intermolecular force that molecules can experience. So this is going to require energy to break. So once again, step 1 and step 2 are both requiring energy to separate particles. Step 3 is a little bit different because it's allowing the solute and solvent to interact. So now you're going to have bonds breaking. And when you get these new particles together, you might start to see new attractions and new forces holding those particles together. So the formation of a bond, instead of requiring energy, is going to release energy. I guess I should say the formation of a bond, to be specific, releases energy. So we see that energy is involved in these 3 steps of making a solution. So when we put all of these steps together, we're going to see that there's an effect on whether or not a solution will even form if we mix 2 different substances together. So we've got an example right here, a drawing, I guess I should say, not an example, an illustration of step 1, step 2, and step 3. We've got the expanded solute, the expanded solvent, and then we've got them together. And we did talk about this on Friday, those new intermolecular forces, or IMFs, that occur between the solute and the solvent particles. Moving on, since step 1 and step 2 require energy, and step 3 normally releases energy, that means step 1 and step 2 are going to be endothermic processes. Endothermic meaning that you are inputting energy to get it to happen. And then step 3, instead of being endothermic, is going to be exothermic most of the time. So we call changes in energy enthalpy. So the heat of a reaction or the heat of a solution is called enthalpy, which is really just a fancy word for a change in an energy amount. So the change in enthalpy for a solution, this is like your total amount when all is said and done before and after, is going to be equal to your change in energy for step 1, for step 2, and step 3 added together. So that's what these symbols right here in blue are referring to. It seems like a maybe complicated equation, but really it's not, and it's not something that's too difficult to wrap our head around. If you add up the total energy amounts involved in all 3 steps, you're going to get your total energy change for the entire process, which we call the change in enthalpy of a solution. So when our change in enthalpy, our change in energy rather, I should say, is positive, that means it's endothermic. So I used green on the previous slide to highlight that. I'm going to do that now. A positive sign is referring to an endothermic. I want to say reaction, just because it flows off the tongue, and we will have endothermic reactions, but that may not be the best way to describe this. So endothermic process might be better. When the enthalpy or change in energy is a negative number, I'm going to highlight that in blue. That is referring to an exothermic process where energy was released instead of absorbed. So we have different charts that show what this looks like. In general chemistry, you probably saw a chart, in fact, not probably, you did see a chart like this where it's referring to that change in energy. You have a very beginning and you have a very end. Now, The difference between the very beginning and the very end is going to determine whether or not that process was endothermic or exothermic. But there's steps in between the very beginning and the very end. And this is where students and even sometimes teachers get confused. I definitely got confused with this when I was learning it for the first time. It took a few times for it to start to make sense. So step 1 and step 2, we said are endothermic processes because they absorb energy. This arrow pointing up is showing the absorption of energy, and you can see my energy is going from a medium value, let's just say, to a higher value. That means I gained energy. So breaking bonds is requiring an input of energy. Then once my solvent particles get together and start to form new bonds, I see that that process is exothermic. I see that it's exothermic because my energy is going from very high to very low. So that energy loss must have gone somewhere. If it's no longer in the particles, that means it left the system. It was released to the surroundings. That's an exothermic process. That's a release of energy. Now, overall, this is where I use that term net release on that Friday before we left. Overall, my process is exothermic as well for this example on the left. Remember, these are just examples. Now, someone who doesn't know that there's a step 1 and a step 2 and a step 3 and is just looking at the very beginning and the very end might see that since this is overall an exothermic process, they might say something along the lines of, oh, I broke bonds and I released energy. So breaking bonds releases energy. But what they're not noticing or what they're not seeing is that there's steps in between that very beginning and that very end. And the breaking bond step is an endothermic process, putting in energy to break those bonds. Now we got an example over here on the right that still shows step 1, step 2, and step 3, but the difference is that it's showing a very different beginning and a very different end. And what I mean by that is, okay, our very beginning is still in the middle, but our very end is no longer a really low energy value. Our very end is actually a little bit higher than what our very beginning looked like. So step 1 and step 2, still an endothermic process, breaking bonds still absorbs energy. Step 3 is still exothermic, it's still releasing energy, but it's not releasing as much energy as what we saw for step 3 in the previous example. In this example, step 3 releases a very small amount of energy. So overall, my overall change in energy appears to be endothermic. It appears that overall, I had to put in energy to get this solution to form. So we got to pay attention to these 3 steps and how do these energy amounts compare, and does that make a difference on whether or not a solution will even form? So we talked about this example on Friday. I don't want to go over it again for the sake of time. So I'm just going to go straight into this table because this is truly the last thing we talked about. We talked about how your net change in energy or your net enthalpy is going to determine your outcome. If there is a huge change in energy, you are not going to see a solution form, whether that is energy going in or energy, well, no, if that's energy going in, you have to put in a large amount of energy overall to get this solution to form. It's not going to form spontaneously. It's not going to form on its own. That means you're kind of going against nature, trying to make something happen that isn't going to happen. Kind of like when you take 2 magnets that are the same end magnets and you try to push them together, they repel, right? Same thing if you take a positive and a positive charge, you put them together, they repel. This is kind of the same idea. If you have to put in a large quantity of energy to get a solution to form, you're trying to overcome bonds and intermolecular forces that are more stable than the solution that you're trying to form. So if we look at our types of substances that we're mixing, we see that when we have a polar substance mixed with a polar substance, a solution forms. If we have a nonpolar substance and a nonpolar substance, a solution forms. When we try to mix a nonpolar and a polar substance, so this row here and this row here, we see that the net change in energy is very large and that no solution forms because of it. So we can make an assumption that substances that are the same polarity are going to mix. A nice way of saying it is like dissolves like. So in general, one factor that favors a process is an increase in probability of the state when the solute and solvent are mixed. Gosh, that's a mouthful. So let's break it down. So one factor that favors a process is an increase in probability of the state. Gosh, what does that mean? So an increase in the probability of the state is talking about stability. Some particles are more stable when they're bonded to other certain types of particles. What I mean by that is you're not going to see a nonmetal and a nonmetal form an ionic bond. We know why this is. They're both very electronegative. One is not going to give up an electron. But when you really think about what holds atoms together, protons and electrons, protons and neutrons, oppositely charged particles being attracted to one another at the very the smallest level that we can consider with atoms and with molecules, they are most stable bonding in a way that the electrons can be easily attracted to the protons, right? They can be as close as they possibly can. So that's why it doesn't really come from a place of an atom wanting a certain thing or not wanting a certain thing, but it really comes from, are these electrons as close as they can possibly be to the protons of this atom and this atom? And we kind of refer to that in a blanket term as like stability, right? So in certain cases, when you're talking about polar and nonpolar, if you've got a polar molecule, it's going to have a positive and a negative side. If you've got a nonpolar molecule, that means you've got no sides that are positive and negative. There's going to be forces that are taking this polar molecule towards other polar molecules. It's just going to happen because there's going to be an attraction between a positive and a negative. So even though this polar molecule is surrounded by these nonpolar molecules, eventually it's going to start experiencing intermolecular forces or attractions that are going to separate it out of the nonpolar molecules. So when you're talking about stability, it just really means that everything is behaving as best it can to follow attractions or to meet attractions. So processes that require large amounts of energy, once again, you're trying to overcome nature, don't occur. So our simple phrase that we're going to say over and over again is like dissolves like dissolves like dissolves like. So there's a lot of things that affect whether or not one thing will dissolve in another. We talked about the amount of energy. We talked about the structure of the molecule. So polarity is referring to this whole like dissolves like phenomenon that we've just discussed. But there's other things too that affect solubility. Things like pressure. When you're at higher pressure or lower pressure, how is that going to affect a substance's ability to dissolve? And even temperature, when it's really hot outside or when it's really cold outside, how is that going to affect your temperature or your solubility? Okay, so structure, referring to, once again, polar versus nonpolar, leads to two different types of substances, hydrophobic and hydrophilic. Hydrophobic is a word for water fearing. These are usually nonpolar substances. Once again, because of the lack of dipole-dipole interaction, the water molecules are just going to separate out. It's not really about like a repulsion as much as it is those water molecules are going to be attracted to other water molecules, and they're not going to separate just because there are other molecules around that have no positive or negative end. So you can put them in the same vicinity, but those water molecules are going to navigate towards other water molecules. So we call it hydrophobic water fearing. Just because they don't mix. It's not really a repulsion per se as much as it is a lack of attraction between the two different types of substances. Hydrophilic is not due to the lack of dipole-dipole interactions, but the presence of dipole-dipole interactions. So if you throw in molecules that have a positive and negative dipole because they are polar, then those water molecules are going to separate and become attracted to the positive and negative ends of those polar substances. Now, pressure affects solubility in a lot of, not a lot of different ways per se, in one simple way. It doesn't really have an effect on solids or liquids. It's really an effect on whether or not gases will mix with liquids. Now, you might be thinking to yourself, when would you ever take a gas and mix it with a solid or a liquid? That makes no sense, but you actually have experience with it all the time. And I know I personally do because I have an addiction to soda. Diet Dr. Pepper is my favorite. The vanilla cherry, you should try it. It's really good. Actually don't. It's very unhealthy. Don't foster any addiction to soda like I have. It's bad. But all carbonated beverages are solutions between a gas and a liquid. Carbon dioxide and, typically water is the solvent of soda. They don't mix it with anything else other than, not anything else. Water is the main component. I'm tripping over my words and I'm having verbal diarrhea. Anyway, have you ever wondered how they get the carbonation into the liquid? They have to do it under enormous pressure, which is why when you open up your soda, you hear that nice sound as gas escapes. The way that they get gas to dissolve into the soda is by placing it under enormous amounts of pressure and then capping it and keeping it under that pressure until someone's ready to drink it. But as soon as you release the pressure, the gas starts to separate from the soda, and you have evidence of that with the sound that you hear, and you also have evidence of that by leaving the soda out. It starts to lose its fizz. It starts to lose its bubbles. When you have a big 2-liter bottle of soda and you don't drink it in a reasonable amount of time and you go back to drink it, you notice that there's a difference. It's not as carbonated as it once was, because when it's not underneath that pressure, the gas is not going to stay mixed with the liquid. So we can describe this relationship with an equation called Henry's law. So C is your concentration of the dissolved gas. Highlight that. And then K is your constant. Your constant is going to depend on what type of gas and what type of substances you're working with. So it's not necessarily going to be the same every time. And then P is your partial pressure of a gas or solute, or I'm sorry, gas solute above the solution. So partial pressure is referring to the fact that it's going to be a mixture. Your gas that's above the solute or above the solution is going to be a mixture of air and all the gases that are in the air. So specifically, the partial pressure of that gas that you're trying to mix in to the solution is going to be what's key here in this equation. So your amount of dissolved gas is referring to your concentration. Is directly proportional to the pressure above the solution. So higher pressure means higher concentration, a higher amount or a larger amount of gas that you can dissolve. So we've got an illustration right here on the next slide that's kind of showing this relationship. When you have low pressure, the gas particles are unlikely to sift into the solution. But when you increase the pressure, you see that they're more likely to dissolve into the solute or into the solution. So moving on. Now, temperature also has an effect on solubility. Specifically, this slide is referring to aqueous solutions. Now, I've used the word aqueous before with you guys, maybe once or twice. If you had me in honors chem before this, you've definitely heard it before. Aqueous solution is referring to solutions in water. That's what aqueous is referring to, like aqua. So although the solubility of most solids in water increases with temperature, the solubilities of some substances decreases with increasing temperature. So this makes predicting temperature dependence of solubility very difficult because you aren't always going to be sure if increasing the temperature will increase the solubility or vice versa. The solubility of a gas typically decreases as the temperature increases. And it kind of makes sense when the particles are moving more quickly. I'm referring to the gas particles here. It's unlikely that they're going to embed themselves in the solvent or in the solvent. It's more likely instead that they will bounce off and continue on their merry way because of just the momentum that they have moving at those great speeds. Oh, wrong way, right here. So we've got a graph on the next slide that's showing the relationship between solubility and temperature. And as you can see, it's not the same every time. For a lot of things we're familiar with, like sugar and other various salts, potassium nitrate might not be something you're super familiar with, but it is an ionic compound, so it's very similar to salt. We see that the solubility is increasing as the temperature is increasing. The only time that it's not is for a few substances that I'm going to highlight in pink is for sodium sulfate and cesium sulfate. So if we were looking for patterns, we could maybe make an inference, or a hypothesis might even be better, that larger ionic compounds are less soluble at higher temperatures, because that's what it appears that these red lines are illustrating. But this is just an example about how difficult it is to predict what temperature is going to do to solubility without a graph like this one. Now, these are the solubilities of several gases as temperature is increasing. For the gases, there's a little bit more consistency. We see that as temperature goes up for the gases, the solubility goes down. And once again, it has to do with the fact that those gas particles, when they're moving at higher speeds, are going to be more likely to bounce off of the solvent rather than to mix with it. Oh, geez, I didn't know how well I was doing. So this is the last slide of our notes. I appreciate you for sticking with me and going through all of that recap. I really missed teaching you guys. So stay tuned for more videos like this one.